platform today. Here, the goal within Ether is to empower enterprises that are going through their Industry 4.0 transformation journeys. But first, let me take a minute to tell you about our journey so far. You may know that SDN was invented at Stanford and Berkeley about 15 years ago now. And as SDN was starting to get early traction in the industry, especially at Google, the SDN founding group at these universities decided to spin out ONF to evangelize SDN and build open source SDN platforms for the industry. And over time at ONF, we have built multiple open source SDN platforms and solutions. And these are now at different stages of adoption by the industry. And during the past couple of years, as part of this, we have been building Ether as 5G connectivity as a service for enterprises, and have Ether be seamlessly part of the edge cloud and hybrid cloud solutions. And I lead this initiative at ONF. As part of it, we have also received $30 million in funding from DARPA, in collaboration with Stanford, Princeton, and Cornell universities. The goal of the DARPA project, it is called Pronto, is to take Ether to production readiness and deploy it on university and enterprise campuses. And we're just about past 1 year into this project. And we have already deployed Ether at close to 15 sites and have been operating it with pretty good performance and availability. And recently, our board, with the support from DARPA, has decided to spin out Ananke to commercialize Ether and offer it as a solution to the market with SLAs to accelerate the adoption of 5G and 5G-enabled solutions for Industry 4.0 and broader digital transformation. So with that introduction out of the way, let us proceed. As you all know, we are at the cusp of the next enterprise digital transformation, Industry 4.0. And to summarize, Industry 4.0 is the automation of everything era, automation of manufacturing, machinery, and processes towards achieving higher quality solutions and operations with lower cost and faster time to market. It is also the era of multiple clouds for enterprises. So Industry 4.0 needs to deliver on this automation using cloud economics while ensuring enterprises are not locked into one specific cloud. And Industry 4.0 solutions need to bring about faster innovation and be able to adapt to changes in enterprise strategies, in where they are in their transformation journey, and also in their physical environments. And Industry 4.0's automate everything paradigm is only possible with a corresponding connect everything. So Industry 4.0 is all about closed loop automation, and this automation is software driven. The applications that enable this automation run from the enterprise virtual cloud that the enterprise owns and manages according to its own strategy. These applications leverage analytics from the physical environment collected via a group of connected devices and apply insights for automation by controlling a group of connected devices. That connectivity is really at the heart of Industry 4.0. But not just any connectivity. A software-driven closed-loop automation needs software-defined connectivity, one that is programmable and adaptable. It also needs to enable consistently and predictably high-quality mobile connection, potentially at scale. So Industry 4.0 really needs a software-defined 5G. Then applications, software-defined 5G connectivity, and virtual clouds are really interwoven in Industry 4.0, and hence they need to be interoperable. And not just interoperable, but also aware of one another's operational states, so that Industry 4.0's automation is optimally beneficial for the enterprise. And for every component of this architecture, it is the enterprise that needs to be in control. So let us build this out. We said enterprises want control of their own virtual clouds. An enterprise with multiple locations will potentially have multiple on-prem edge clouds. And it is the multi-cloud era, so it is likely that enterprises will also use multiple hyperscaler services for their operations. Then an enterprise-specific set of securely interconnected clouds, on-prem and central, with the enterprise at the helm for management, constitute the enterprise virtual cloud. And each of these clouds that make up the virtual cloud obviously needs to have a cluster management for cloud resource and workload management. And further, a centralized means of controlling all of these clusters is needed so that enterprise-wide policies may be applied and lifecycle managed everywhere. Once the virtual cloud is operational, we can bring in the Industry 4.0 applications that drive the automation for the enterprise. And depending on the use case, these applications could run on-prem or in a central cloud location, or both in a distributed manner. As the enterprise's Industry 4.0 transformation progresses, more and more automation will come to life, all via different and stackable applications. And cloud economics will enable the enterprise to elastically scale the rollout of this automation. The last piece is the customizable and adaptive private 5G connectivity. And just like the virtual cloud management, the enterprise needs to be at the helm of connectivity management, programmatically setting or updating their connectivity policies and centrally executing them across all of their premises. So this takes us to Ether, ONF's open source 5G connected virtual cloud platform for the enterprise transformation. Ether provides a software-defined 5G tightly integrated with the virtual cloud, one that is top-down and end-to-end programmable. This programmability extends from the RAN to the edge cloud fabric to mobile core and is conducted in a coordinated manner end-to-end using its runtime operational controller, or ROC. The programmability enables Ether to extract fine-grained telemetry, allowing for a programmatically verifiable solution and closed-loop control for automated adaptation to a variety of factors. And these unique features bring a number of attractive capabilities to Ether. Ether is resilient to hardware and software failures, to unexpected and bursty congestion in the network, and to external attacks in the form of denial of service or exfiltration attacks, for example. And it is also programmatically operationalized using cloud principles. And it programmatically exposes APIs to Industry 4.0 applications for optimized end-to-end operations. More on that in a minute. So with Ether, the foundational starting point for us has been to make 5G a solution as simple to consume for the enterprises as Wi-Fi is today, and augment the standard 5G features with features that our software-defined approach brings. Ether is flexibly layered on enterprises' existing edge cloud preferences. So as such, it can run on its own virtual cloud platform or any one of the hyperscaler edge cloud and hybrid cloud solutions, including those from Google Cloud, AWS, and Azure. And it can also run on enterprises' own managed Kubernetes. So let us look at the Ether architecture in more detail now. Consider an enterprise going through Industry 4.0 transformation using the Industry 4.0 applications. These applications clearly need connectivity to a variety of devices on-prem. So to this environment, we bring in Ether. Ether uniquely enables a software-defined 5G and is distributed across the edge and the central cloud. At the edge, we have the components that give us programmatic control of the RAN, the edge cloud fabric, and the mobile core. And of course, we have the user plane function of the mobile core at the edge, giving us a local breakout. And this is especially for the enterprise. This is crucial because the enterprises want to have the power to localize any traffic within their own premise to gain complete control on traffic isolation and data privacy. And clearly, a local breakout would also enable us to provide a more performant 5G connectivity towards these edge applications that are co-located with this UPF. And we have pre-integrated small cells from our ecosystem partners into the Ether platform. And when they allow, we programmatically control them using ORAN interfaces. And with programmable RAN, the Ether platform uniquely provides a coverage with consistently high performance, and it brings about the extension of quality of service and programmatic network slicing to the RAN. The central component of the architecture enables us to leverage the rich telemetry that we collect from the RAN, the core and the fabric components. And it conducts end-to-end coordinated control and management accordingly using our portals. But also the central component also includes the NAI-based closed-loop control which uses event correlation and automated reaction to optimize customer experiences and simplify operations. And we also expose highly abstracted 5G connectivity APIs to Industry 4.0 applications. So I will give you more details about these APIs as they are unique for the Ether platform. But under the hood, we really have a system composed of multiple deeply programmable and tightly integrated components. We have SD Fabric for edge cloud network control, SD-RAN for programmatic small cell control using ORAN interfaces, and SD Core for programmatic 4G and 5G mobile core user and control planes that are runtime configurable. And each of these components is a standalone open source project within ONF. The coordinated programmability of these components is overseen by our runtime operational controller. And Ether includes the necessary interfaces to run on and be integrated with hyperscaler and hybrid cloud solutions that make up the enterprise virtual cloud. And for bare metal deployments, we have our own virtual cloud solutions. So with this, let us now look at the APIs that Ether exposes. So this is the Ether stack getting layered up. So first off, via open SDKs provided in multiple languages, Ether offers APIs and libraries to RAN control application developers who may wish to bring in innovative solutions towards automated RAN telemetry collection and control. Similarly, it offers open APIs to SDN and P4-based edge cloud fabric control application developers who may wish to bring in innovative solutions towards telemetry collection, network verification, and control towards enhanced performance, security, and troubleshooting capabilities. And we also have open APIs for our mobile core towards developers who may want to integrate it with platforms and solutions such as eSIM management platforms, LDAP integration with directory solutions like Active Directory. And these three components also expose APIs towards integration with OSS and BSS platforms, We use these APIs internally, obviously, to integrate them with our runtime operational controller. Next are the system-wide APIs. We expose APIs towards customer portal development. And obviously, we also use these internally, but they may be utilized to develop unified portals that allow customers to monitor and control cloud, SD-WAN, and private 5G solutions. And towards bringing autonomy to the end-to-end system, we expose APIs towards developers who want to build AI and perhaps ML applications for end-to-end connectivity control and management. These applications would not only result in better overall performance, but also simplify operations, minimizing the need for human intervention. And last but not least, we expose APIs towards Industry 4.0 application developers. So from an autonomous network perspective, this is important. When you think about it, a potential enterprise will want a 5G network to enable an Industry 4.0 use case. This itself is an enablement of an autonomous solution, and 5G is only a part of it. So for an overall optimized performance, connectivity and autonomous Industry 4.0 operation need to be considered together. And for Industry 4.0, this is really, from that perspective, a particularly important API. So let's get maybe even one step deeper into this. So while developing an Industry 4.0 application that enables enterprise automation, the developers use already certain tools that are available to them. There are IoT platforms and AI ML platforms. But there is a critically important component that is missing in the toolset available to these developers. And this toolset is the one that would provide insights on connectivity between the application and the devices it monitors and controls. One that provides information on connected device identity from a 3GPP perspective, its location, its state, whether it's asleep, it's active, non-operational, etc. And one that enables direct control of this connectivity. And also one that gives a detailed telemetry information for this connectivity, for best overall experience. And the Ether platform is really poised to fill this void. And with an open set of APIs, SDKs, we aim to bring 5G connectivity awareness to Industry 4.0 applications, and thus optimize the overall Industry 4.0 experience. So with Ether, the 5G infrastructure one would deploy would not only include the 5G small cells, but also Ether's containerized 5G core user and control plane resources across multiple clouds. The software-defined nature of Ether empowers the enterprises and solution providers like Ananke to offer these resources as network as a service to mobile network operators, MVNOs, and other operators who may wish to use them. And this, you can view them as the next generation, a cloudified version of the neutral host paradigm. So let us now take a look at how the Ether stack layers up. So as I have mentioned, for bare metal deployments, Ether comes with its own hybrid cloud solution integrated with 5G components. So we start with the infrastructure on-prem in central cloud. And for each cluster in the virtual cloud, we have cluster management as well as secure interconnect components. And running centrally, we have management of all clusters in the virtual cloud. Layered on this, we have Ether components that enable 5G connectivity. And next, we have the operational tools, the monitoring, logging, and alert platforms, and portals that allows enterprises to customize and operators to control and maintain the network. And running on top, we have our CI/CD toolchain. And of course, Ether's virtual cloud platform can also host Industry 4.0 applications and platforms. And these need not follow our CI/CD tooling, but rather can have their own lifecycle management. And Ether's 5G connectivity leverages the CBRS spectrum in the US. So a third-party operated spectrum access system, or SAS server, completes this stack. So Ether can also run on hyperscaler services. In our pilot network, we also maintain a complete Ether operation, both on-prem edge and central cloud components running on Google Cloud's Anthos. But Ether can also run on AWS and Azure Arc. So let us very quickly take a look at the individual building blocks of Ether. Ether's SD core is a fully disaggregated solution and is composed of containerized components. It enables both 4G and 5G, both as standalone and non-standalone, and it enables connectivity of all of those options. And as you know by now, it is configurable in runtime via an extensible set of APIs. Now, the SD core has two distinct UPFs, and each deployment may select one or more to be instantiated for configurable set of network slices. So we have what I would call a P4-based dual-core UPF and a containerized dual-core UPF. So by dual-core, I mean these UPFs can communicate with both 4G and 5G control planes and serve both 4G and 5G sessions at the same time. The dual-core user plane functions are implemented using a disaggregated architecture, as you can see. This architecture includes a common control interface function, which we call a PFCP agent, and an implementation-specific packet processing and forwarding function. So the packet processing and forwarding function for the P4-based dual-core UPF includes a UPF-specific P4 application running on a P4 programmable switch that specifies exactly how packet forwarding and processing, including GTP tunnel encapsulation and decapsulation, should be executed for both downlink and uplink. And another component is ONOS, our SDN controller, that installs these table entries onto the switch based on the information received from the PFCP agent. And the next component is the UP4 application running on the ONOS that communicates with the PFCP agent and engages the SDN controller ONOS to install these forwarding rules. And last but not least, a buffering module that is used to buffer the incoming packets towards a device that is in idle mode or when the device is going through a handover. And the packet processing and forwarding function for the containerized dual code UPF has been developed on the Berkeley extensible software switch, the BESS architecture, as a containerized software switch. Now let us take a look at the SD-RAN component. So at the center of this component is an open source cloud native microservices-based near real-time RAN intelligent controller. This is based on, again, the ONF SDN controller, ONOS. And included in this is also an SDK, as I have already mentioned, in actually multiple programming languages, aiming to provide the necessary drivers and interfaces to the developers so that they don't need to worry about the understanding of the innards of the RIC. And a number of XApps running on this RIC are also under development by our ecosystem. And a fair number of these XApps are ML-based. And these XApps leverage the ORAN specified E2 service models clearly. But some also require new pre-standard service models, which are under continuous development by the SD-RAN community. And once developed and implemented for initial fine-tuning, they are continuously being contributed to the ORAN Alliance. And ARIC also includes A1 and O1 interfaces towards the SMO and cloud. The microservices that make up the RIC include an XApp subscription service, network and UE network information-based services, distributed data store service for high availability, operator service for cloud operationalization, southbound and northbound ORAN interfaces terminations, and extensible service model support service, SDK services, as well as a command line interface service. Now, the next component that Ether has is SD Fabric, and it enables a P4-based SDN control of the edge cloud fabric. It leverages our open source SwitchOS stratum that enables programmatic control of the programmable switches and ONOS as the controller with control applications that control them. In the context of Ether, one of the main benefits of a programmable edge cloud fabric is its capability to bring per packet in-band network telemetry for all traffic, including 5G traffic. This is used in Ether to bring heightened visibility of the network to the customers, along with higher performance through automated control and enhanced security via automated real-time reaction to potential attacks to the network. And the runtime operational control is a private network optimized cloud native and microservices based SMO or OSS/BSS. As such, it consumes abstracted telemetry from all of its components and via portals and applications adapts to the changes in the environment. So when I started, we had built the desired 5G connected virtual cloud architecture for enterprises. Now that we understand what Ether is, what its building blocks are, and how Ether can be consumed, let us see where its components reside in this architecture. So when Ether is consumed on bare metal, we can see that its components enable the private 5G connected enterprise virtual cloud. And similarly, when it runs on cloud services from hyperscalers, its components enable the private 5G connectivity across all enterprises, all sites of the enterprise rather, all managed centrally. So let me also introduce to you the tooling we have to operationalize Ether. Over the last 2 years, we have been building a CI/CD pipeline for Ether that enables us to bring automation to building, testing, and deploying all of the Ether components continuously. So here you see the CI pipeline. And one thing to note is that we have also incorporated GitOps in our CI/CD tooling so that the Ether operations team can establish and update infrastructure and application configurations towards automated deployments as part of the GitOps tooling. And the images, manifests, and infrastructure and application configurations are collectively used for the CD portion of the CI/CD toolchain. The automated infrastructure configuration updates empower us to treat Kubernetes infrastructure as code. And thanks to our CI/CD pipeline, we can now deploy a new Ether edge remotely in just a few hours. The tooling also enables us to maintain our operations, handle potential bugs, introduce new features towards a highly performant and highly available solution automatically in this time. And I mentioned when I started to talk that the Ether solution has been operational for the last 2 years as a pilot network. We have seen our global footprint grow during this time. So indeed, we now operate Ether in about 15 locations around the world, and we have a number of new sites in the pipeline. And we have already achieved multiple nines availability at these sites. So just about less than a month ago, we have operationalized a field trial with Deutsche Telekom in Berlin. This is a combined 4G and 5G network with Ether, one that is fully disaggregated, software-defined, containerized, edge and hybrid cloud enabled, and one that is ORAN-based. This network is a multi-vendor one and is leveraging both open source and open but proprietary components. So the trial is taking place in the courtyard of the DT Digital Innovation Arena in Berlin, where an edge cloud has been deployed and interconnected with a hyperscaler central cloud. And connected to this edge cloud, we have 4G and 5G small cells that are disaggregated into RU, DU, and CU components. And in the case of the 5G network, that conform to ORAN's front haul and mid haul interfaces. And furthermore, these small cells are programmatically controlled using Ether's near real-time brand intelligent controller. And we have multiple applications running on this RIC from the ecosystem that enable mobile link telemetry collection, as well as control and management of the mobile link. And the fabric of the edge cloud is P4 programmable and is controlled by ONOS, and a suite of fabric control applications that make up Trellis give us the IP forwarding control programmatically. And the 4G and 5G network leverages the open source mobile core from SD Core. And we have a number of user plane functions that enable us to exercise network slicing. And the hybrid cloud-enabled solution is fully containerized and is managed by Ether's CI/CD and virtual cloud platform that oversees, in addition to 4G and 5G connectivity, container management, cluster management, and operational tooling. And this field trial is operationalized actually thanks to the participation of a large number of vendors, including Intel, Radisys, Foxconn, and XApps from Facebook, AirHop, etc. So with that, let me end my talk with some takeaways. Industry 4.0 is all about automation and has connectivity, specifically 5G connectivity at the heart of it. And it needs a clean slate private 5G solution that are built from the ground up with Industry 4.0 in mind. We are also in the multi-cloud era for enterprises. So these solutions need to be flexibly layered on all virtual cloud solutions. And 5G and virtual cloud solutions should be simple to deploy and simple to operate. And at the same time, they should be performant and reliably so at scale. And private 5G solutions should provide a rich set of APIs towards Industry 4.0 applications for an overall optimized end-to-end experience. And they should be highly customizable and be programmatically adaptable. And all of this has to come at low cost. And our open source Ether platform provide a software-defined end-to-end private 5G connected virtual cloud solution to enterprises. And it satisfies all of these requirements. So with that, let me stop here and thank you for your kind invitation to present at your event and try to answer any questions you may have.
All right, thank you very much. And thanks for the presentation. I think it was an impressive piece of work, all the components and all the different elements that come together to realize these very complex networks. Let me see. All right, there's one question in the chat that is asking if there is any document or information on the API structure for Ether.
So the API structure, we are usually, I mean, we're at fault here. We're usually much faster in development than documentation. So the API documentation is in progress as we speak. So please be on the lookout. And I have noted your name, so I will reach out to you once we have the documentation with the link.
Thank you. And we have another question that is asking about the frontal. So if I think if SD-RAN has a frontal components using the CPRI part or not?
Yes, yes, it is. Right. It is fully ORAN compliant, and we use eCPRI. Yes.
And the third question is this: how is reliability and availability going to be handled with such a dependence on the cloud?
So that's an excellent question. So we have to start thinking about availability and reliability from a cloud perspective, and stop viewing it as vertical hardware silos where we bring in redundancy. So think of Google or Facebook applications and how they bring about reliability. So moving towards cloud native, which is something that we are very fast progressing towards. The last piece actually is a number of services within mobile core. Once you have a cloud native solution, the redundancy comes into play, and with necessary cloud architectural interfaces, you can bring about reliability. And in a multi-cloud setting, you can even bring about redundancy across geographies as well.
Thank you. And there's another question on Zoom. So in the DT, the Deutsche Telekom test, what kind of throughput are you able to see and to achieve in uplink and downlink?
So I don't have the numbers in front of me right off the bat, but I can tell you that this was, let me tell you, this is running on a spectrum that is, as you may know, in Germany, there is dedicated spectrum for enterprises. So we are using a dedicated enterprise spectrum for the trial. It is continuously ongoing. And there we are using a 10 megahertz bandwidth. So that puts it on par with a typical 4G data rates, maybe slightly higher because we don't have any interference in that spectrum.
Right, got it. And I think this availability of spectrum dedicated to private network is something very interesting. There's another question, and I think it's going to be the last one. So what are the network functions in the core that have been implemented with respect to all the network functions that are in principle available in a 5G core?
So from a 5G core perspective, we have obviously AMF, SMF, AUSF, NSSF, PCF, UDR, UDM, and NRF implemented today. And of course, UPF in multiple flavors.
All right. And just one last question from me. So can you comment on what would you see as the main challenges that you face in terms of implementation for this system? So it's a system that appears to be quite complex with a lot of moving parts. So what are the main challenges that you saw during the implementation phase, and you are still seeing probably?
We see many challenges actually along the way. But in the interest of time, maybe I can summarize it as such. 5G is moving towards a cloud, software-centric, cloud-operated service, right? And in that setting, the cloud era has moved in a more organic way, and while 5G is very standards compliant. And marrying these two, especially the standards notion of how a cloud 5G should run versus how hyperscalers traditionally run their services, there are actually mismatches there. So that brings about certain issues. That gap is an important gap to fill. Another important thing is, the ORAN interfaces are being standardized as we speak. So the solutions for ORAN compliant, disaggregated and programmable 5G RAN are only now coming out, and ironing out the stability in both solutions and also with the specifications is something that is challenging. I mean, while we were doing DT trial, for example, the DU component specifically ended up running on a brand new Intel CPU. And it was so new that there was no DPDK support for it. So we had to go about and do that. So these are sort of the challenges because we are really going through a new era. Hardware and software is brand new, and we have to do a lot of things all at once.
All right, thank you very much. So in the interest of time, I would say there are still a couple of questions on the chat. Maybe you can answer them directly on the chat. And I would like to thank you again for this very interesting talk and for participating to the Open 5G Forum.